Alright, so today we're going to be going over how to solve systems of differential equations. So let's come up with an example. Let's say dx over dt is equal to y, and dy over dt is equal to x. Alright, so this is going to end up with the general solution because we're not given any other information. So we're just going to be going over how to find the general solution today. The first thing we're going to do is we need to come up with a variable vector. And so that's easily going to be xy. And so to counter that, we also need to have a differential vector, which is going to be this, right? Or you could say that that's the same thing as dx over dt and dy over dt in the vector. Now we need a coefficient matrix. And that's fairly simple, 0, 1, right? No x, 1 y, because we do x first, then y, and then 1, 0. So easily this ends up becoming dx dt is equal to 0, 1, 1, 0 times x, y. And then, with that, now we just need to solve. So how do we solve? Well, we need to find the eigenvalues of the coefficient matrix. And so I'm sure all of you remember how to do that. That's just finding just setting the determinant of a minus lambda I is equal to 0. And we know a minus lambda I here is going to be equal to negative lambda 1, 1, negative lambda. And so the determinant of negative lambda 1, 1, negative lambda is going to be equal to 0. So then we can solve that. We know that negative lambda times negative lambda times negative lambda is lambda squared. It's going to be minus 1, and that's going to be equal to 0. And so lambda squared is equal to 1, and so lambda is equal to negative 1, 1. So those are our two eigenvalues. And so we're going to set our first eigenvalue to negative 1, and our second one to 1. So now we're going to solve for the eigenvectors to this. So this ends up giving us, in our a minus lambda I, negative negative 1, which is going to be 1, 1, 1, 1, and then solve for that when ax equals 0. Alright, well that can cancel out, and so we end up with x1 plus x2 is equal to 0, so x2 is equal to negative x1, and then just plug that into our solution vector. Whoops. Just like that. And so then this is v1. Then we do the same thing here. We can multiply this by negative 1, cancel that out, and so then we end up with negative x1 plus x2 is equal to 0. x2 is equal to x1, plug that in. And there we go. Now we have our second eigenvector. Now, the general solution is always going to be in the form of x of t is equal to c1 e to the lambda t, e to the lambda 1t, v1 plus c2 e to the lambda 2t, v2, and then so on if there are multiple eigenvectors. So that is known as the general solution. So let me just come up with a color for that. We'll do red. That is the general solution to a system of differential equations. Let's go back to white. Alright, so now let's plug in what we've solved for. Now before we can simplify this further, we need to check to see if they are linearly independent. vectors in the solution. And so that's going to be equal to that, and then we want this to not equal 0. If it's not equal to 0, then we know that they're going to be linearly independent. And so now we need to just solve the determinant of this. That's e to the negative t times e to the t is going to give you e to the 0, which is 1. And that's going to give you a negative 1, so that's 1 minus negative 1. And that's equal to, you're kidding me. And that's not equal to 0. God damn it. So we can say that they are independent. I don't know what's going on with my pen, but it's getting annoying. All right, and so then we know that this is our general solution. And you can simplify that down if you want, but you don't really have to. And that is our general solution.